Welcome everybody. This is the class 22, and we are starting to do real science. So I have this moment after the exam to talk about life. We know that everybody delivered the exam, so the question is, as usual, why? Why is always a good question. In particular, why we are here, where we are doing this thing, and I guess that different people may have different answers, but my answer is we are here to become scientists, people who do science. And my point that I always like to make here, because it's my main difference with some of my colleagues, is that science is not only about making experiments. Experiments by themselves are meaningless. Science is the process of creating knowledge, and experiments are just one part of the knowledge. I mean, if you measure the temperature of the, if you measure your temperature every time, you get a lot of data, but not necessarily a lot of knowledge. You have the same temperature every time of the day, no? And the way to selling the truth is the scientific method. That is what makes science different from other ways. The philosophy, for example, has a different way to look for truth. And the scientific method, I have a plot that I will show you in a minute, is we observe nature and we try to find patterns, things that happen again and again. If I push this, then this happens. If I take sugar, I get fat. I don't know. If I take coffee, I cannot sleep. And this kind of patterns that repeat. Science is essentially about finding patterns and explaining why this pattern happened. And to explain them, we create something that we call a model. And today we're going to speak about models, the simple kind of models. And then we make experiments to test if the models are valid. So essentially, there are two kinds of experiments, if you like, philosophically speaking. One are experiments that allow you to see patterns in nature, like the way that you look every day in the window and you say, today is cold, today is hot, or you find pattern, you know. For example, that January tends to be very cold. Most of days in January are very cold, and July, it's usually very hot. That's a pattern that you notice. And then you create a model, and you say, for example, there are seasons. Seasons are a model. It doesn't mean that there's never a cold day in July or a hot day in January, but it's a general tendency, and you essentially a way to understand the world. There is a value when you go from a list of temperature every day to the moment that you see the big picture. You see, there is summer, there is winter. And then you can make, well, in biology, we can make experiment, but not all science is experimental. I give you three examples: archaeology, geology, astronomy. These are clearly sciences, but you cannot do an experiment in astronomy. How you do? Let's take a star and make a black hole. No, you cannot do that. But you can observe pattern and make models and see if that model fits reality and fits new observation, or even the old observations. Okay. Then, why are I put this phrase: we avoid fooling ourselves. That is a famous phrase by one of my idols, Richard Feynman, and essentially saying that the idea of the scientific method is to look for the truth and not fool yourself. It is very easy to believe that you know something that you don't know. And he even said the phrase that you are the easiest person to fool, because every person tend to believe that what I am thinking is correct because I am thinking it. And that is how we fool ourselves. We do things that are not correct if we are not careful and test it. We believe that I believe that I don't know. You are cooking and there is a pot in the oven and you take it and it's very hot. You burn yourself. Why? Because you believe something. You believe that there is no fire, so therefore it's not hot. But no, it was hot. So scientific method is a way to approach that thing. Like, okay, I don't see fire, but it doesn't mean that the pot is cold. And I have to make a test. You are more careful approaching the things. So why this is important? Let me give you some examples. For example, the basic question that people would like to I mean, one of the questions that people are asking is this one. Do smoke cause cancer? You will always say, I have an uncle who smoked all life and never got cancer. And you also have people that, she never smoked, but she got cancer anyway. So yeah, that is true. So how can you say that smoking causes cancer? Eating sugar, will you be fat if you eat sugar or it's not? What if you eat meat? Will you get fat? Some people believe that the cell phone make brain cancer. Don't use cell phone because radiation, the 5G is a brain control system. Or do you need to pay for very expensive pills, or can the cheapest medicine also help you? I have a friend who believes that taking a lot of vitamin C will prevent cancer. That I think that there are people that believe that vaccines cause autism and things like that. So the role of science, the role of scientists, is to answer these questions. That question, I mean, give a truth answer to that question. So what you are going to do if you keep doing science is looking for the truth. And so truth is super, super important. It kind of the basic nature of our work. So that is why I'm very angry if I see people cheating in the exam. So let's see. Even if you don't work as a scientist, maybe you work in a blood bank or in a food factory or in a, for example, a paternity test. All these questions, even you're not doing like top scientific research, top line or top cutting edge science, you will be answering questions that can affect people's life. And the part of the difficulty is that sometimes experiments fail, and people are tempted to say, no, it was not an error, or sometimes you get a result that is not what you expect. So is my experiment wrong, or people try to cheat? That sometimes happen, but you have to be careful. The basic problem in science is essentially when you lie. It is much better to say that my experiment failed than to say something that is not true. And maybe the most important point is that the model that we have are usually incomplete. We have different ways. Let's say, for example, we in molecular biology, we start with the idea, okay, we start very early, but let's say you have the idea that DNA encode RNA, and RNA code for protein, and the information goes that way. But then you find something like reverse transcription, that you take RNA and make DNA from RNA. So that essentially broke the model, or more than breaking the model, is like improving the model. So when we do science, we have models that are constantly being improved because models are always incomplete. Okay, I will speak about models later, next week. I have more to tell you about models, but models are always incomplete, but we are always updating them. So when people get more knowledge, there is some tendency like, oh, but science don't know anything because they are always changing their mind. And that doesn't mean that we don't know anything. Is that we give a model given all the information that we have today. Tomorrow, we may have more information or better models or better instruments, and then we will see things that we were not able to see before. It doesn't mean that the model was false, it just was incomplete. And the scientific method is the process of improving these models. So you can be wrong, but you cannot lie. Being wrong is not the same as lying. So when people ask me if the question is truth or false, that is not the correct question. The correct question is the question is right or wrong. Your question may be right and still be false. Your question may be wrong and still be true. Truth and falsehood is not about being right or wrong. You can, for example, you can make an experiment, and the experiment may fail for many reasons, and you can say something that is wrong, but you are still telling the truth. So I like to show people, and I would like to know if someone else show you something like this. This is my personal version of the scientific model, and I want to put you in the context. So we are making models in natural science. We speak about nature. That will make natural science be nature. And we start observing. Now, observing the nature depends on the knowledge that we have. If we don't have anything, we just look everything with open mind. But then you start having something. For example, you know, you have a microscope. So you have the knowledge that a microscope or the telescope or some instrument will help you to see something that is not easy to see with only with your eyes. You have instruments. And you have theories that allow you to see, okay, this is what I expect, and I am seeing something expected or something unexpected. And through observation, many observation, you will eventually find patterns. And patterns are essentially like, if I do this, then if I do X, Y will happen. Always Y happen, or most of the time, or Y happens more often. If I smoke, I get cold sick. If I take vitamin C, I don't get a health problem. I don't know. Then it's natural, and I always insist that this is the most important part of the scientific method. You ask a question. The value of the scientific research lays mainly in asking the good question. If you have a good answer, it's better. But it's very easy to have a good answer to the bad question. So through time, you will develop more and more the capability of asking the good question. The basic point. And let me say the other way. I worked a lot of time in a big project with good money and very good researchers, but and we had a lot of observation and we had a lot of pattern finding, but we never had a question. And we spent a lot of time and we lose a lot of time and a lot of money trying to find an answer for a question that we did not have. The question is the essential part. To answer the question, you need an explanation. The explanation typically, I will say always, come in the shape of a model. No, I'm not saying that all models are mathematical models. I'm saying that models are abstraction that you try to explain. Like, for example, you say, we have 4 seasons, and there is winter, and there is summer, and in summer is hot, and in winter is cold. That is a model of the way that the weather behaves. And when people say that weather is changing, it's because the data is not fitting the old model. You make a prediction that you can test. So the experiment here comes in the observation part and in the test part. Pattern, question, model, and prediction, all these are things that you do in your brain or with pen and paper. A thing that you do after the experiment and before the experiment. Then, of course, what makes science special, well, one part is that your model has to be tested. For example, in philosophy, people also find patterns, people ask questions, philosophers are very good at asking questions, and they make models, but they don't have typically a way to make predictions that can be tested. So that is why different philosophers have different models, and you cannot tell which is wrong, which is right, or both may be wrong, both may be right. You cannot even know if they are contradicting each other or not. Then you have something very special in science, that you have a peer review, that your result is validated not because your boss say that you are right, not because you went to the DN and you show in the DN and say, you are right, but because you get to someone equal to you, some other scientist in another place that is not better than you, is not worse than you, is an equal to you, and they check your results, they check your logic, they check all this path, and if they agree, you publish, and that becomes part of the knowledge. What we call knowledge in this context is essentially all that we have tested and validated, and the validation go by this step. Someone has to check your work and agree. So you have to be careful that sometimes we have experiments that pass a test, but they are not peer review. I mean that you have a paper that has been submitted, but if the paper is not approved for printing, then it is hard to make sure. I mean, they have a different value of truth. It's like, until here, they are essentially opinion, okay? If there is a peer review process, then they become part of knowledge. Now, eventually, when this cycle keeps going, you will find that some of this knowledge was wrong, and it's constantly updating. That sooner or later will happen. You get new information and you realize that some experiment had a mistake, or they were incomplete or something. But this is general the way that we are doing. And today I'm going to focus here in how to make models. Okay, so models are essentially the thing that we want to test with experiment. Maybe this is something that I didn't put in the plot. The experiment must be replicable. Replicability is a super important thing, because I mean, if I do an experiment but nobody else can do it, how we know it is true? If I see a pattern but nobody else can see, how we know it's true? You know, there is a story when people discovered X-rays. People were very amazed about these X-rays, and they were trying to explore. And there is someone that found something called the N-rays, with an N. I will let you Google it and see, because it's very crazy. The N-rays. It's not urgent because it's a very crazy story, but essentially it's like some fake phenomenon that people believe that happened. People make mistakes. There is a lot of mistakes, and science essentially learns from these mistakes. So at some point, I want to encourage you to make mistakes. I mean, if you don't want to make mistakes, you will never make discoveries. Most of experiments fail. Most of experiments will not give you valuable insight, but after some failures, you will get something new. And because there may be some variation between experiments, so there is a moment that people should know what is your margin of error. If we had more time, we should speak about this. This is something that I am always worried that people don't think about, the margin of error of their experiment. In physics, for example, all physics is based on this idea of margin of error. In chemistry, probably the same. Engineering is basically controlling your margin of error, the tolerance. Okay, so that is the basic thing that I wanted to tell you, like philosophically, about the scientific method. So let's try to do science with our data. So for this, I am working. Well, we have different data. I will show you some. So, but let's start with the basic data that we have been using. In the last class, we found that it was wise to tell that sex and handness were factors, no? So with this, well, today probably is not important, but I want to remind you that you can have an option here when you read the data. You can add an option saying that the column types, and then you have a function called calls, and then you say the name of the column, and you describe the type. In this case, type factor, and what are the levels. Okay. Otherwise, they will be treated as text, and eventually that will be a point. And you see, for example, date, the columns are type date, type character, type factor. You see? We see that there is something good happening here. We will use that. Not today, but we will use that later. So you have to be aware that when you load the data, it is useful to think what is factor, what is not factor. And then we plot, we plot with this formula. And that is the part that I want you to remember. And that is why I wanted to put the formula in this class. We get this thing, right? So the format is this. You put the vertical and then this symbol tilde in, and then the horizontal. Essentially, you mean that the weight depends on, you read this like depending. We want to plot weight depending on height for the data in the student data frame. Okay? Everybody see what we are doing here, no? There is a little formula here, and the formula speak about columns, and the columns are in this data frame. You have to say which is the data frame where these columns are defined. Okay? So I will show you again the summary that we had last week. Essentially, plot y tilde x is looks very much like plot x comma y, essentially like this is horizontal vertical, this is vertical horizontal, but the plots are nicer. In general, they look better, and the shape is this one. They have good defaults. For example, the names you see here, the names are nice, height and weight. Essentially, this plot look nicer, and they are easy to do. But the main reason that we want to do this is because we are going to use them to make a model. So let's start speaking about models. There are different kinds of models, many different kinds, but one of the easiest, most common, and also most used in biology in general, in molecular biology in particular. I mean, economy is 90% linear model. Psychology tend to be also linear model. There is a big range of things that are done with this because they are super. I mean, they have a lot of power. They are not 100% true. We will see. We will see when but they're a good starting point. The best way to start is a linear model because it's kind of what we expected. Like if I take one, if I drink one glass of Coca-Cola every day and I get heavy by 1 kilo in a year, then if I drink 2 glasses of Coca-Cola every day, I will get 2 kilos extra in. And if I take 10 glasses, I will take 10 kilos. So that is the natural way of thinking. Like if I do more of something, I will get better result. Which is true in some cases, but not always. For example, how we will make a model for this thing? You see that there is a tendency here. We discussed this last week. There is some people that are short and light, and some people that are tall and heavy. And there is a tendency in this line. Clearly, there is nobody that is short and heavy, and there is nobody that is tall and light. Okay, you see this tendency. So we want to see what is that tendency. So when I was a child, I heard somewhere, I have no idea where, that your weight should be your weight in kilos should be your height in centimeters minus 1 meter. Okay, have you heard something like that? If I'm 140, I'm 40 kilos. If I am 160, I should be 60 kilos. If I am 170, I should have 70 kilos, something like that. So that fits exactly the idea of a linear model. Please remember this formula. Y the vertical is a constant A plus B times X. So in this case, the model that I had in my childhood was this one. The weight in kilos is usually to height in centimeters minus 100. Okay? Do you agree? Do you see the...
Yes.
I'm not saying that this is correct, but this is what people told me. I mean, maybe it was an old rule. And not necessarily very bad. And we can try. In fact, I will plot it now. But just, do you agree that this formula is one case of this formula? It's an A plus BX. So what is A and what is B here?
A is minus 100 and B is 1.
Agree? Do everybody agree? Move your heads. Or...
Yes. Yes, I agree.
Good. I have to confess that when I prepared the class, I did it the other way. So I am showing you a little command. After doing a plot, we have a command called AB line to draw a line with A and B. Exactly this formula. A is the constant and B is the slope. Okay? And the line is like this. Not bad. I mean, grow more or less in the tendency that I will expect. So let me introduce you. This AB line is useful to make this drawing in particular. We may not use it very much. People tend to overuse it, but you will see that it's not always the best thing. So this command is, there is a couple of variations. If you want an horizontal line, you can use H. If you want a vertical line, you can use B. But in most of our case, we are using like A and B. Okay, A the constant and B the slope. Okay.
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 Now, let's go deeper into linear models. Okay. The hard part here is decide what is the formula. In this case, I give you the formula. In many cases, the formula will be kind of obvious, but the real science here is to think what should be affecting the height. So, for example, in general, given our data, the data we have, what do you expect that can be used to model the height of a person, the weight of a person? What kind of variable? Do you think that the student number will affect the height of the person or the city of origin? If you were younger, if you were kids, maybe your age will be a good predictor of your weight, no? Younger babies tend to be lighter than older children, no?
Yes.
What else can affect? Here, the basic idea is that we are explaining with height, but I want you to think. Okay, let's talk about that later. We will come back to that question next week. But I give you this question: what can be a way to explain the weight of a person? A way to describe, to predict, if you like, a way to model.
Gender, maybe gender.
Yeah, sex is a kind of the basic thing. Maybe the size of the hand, maybe the age. I don't know. Yeah, I will think that people get heavier when they get older in general. No? Not so much after 20 something, but still, when you stop growing, you start. When you stop growing this side, you start growing this side. Okay, so the model that we have in mind is always this A plus B, but in this case, the Y is the weight and the X is the height. And the question is, which are the best A and B values? Well, I will not enter today in the mathematics of this. I don't know if necessary. Yeah, maybe one day we can, if you want, we can do the mathematical modeling of this. There are a couple of nice ways to show, but essentially, the trick of linear model is that it's very easy to calculate what are the best A and B. Okay, for some definition of best that you have the right to ask. And the point is this: if you plot like this, then you can get the best values using linear model. Same formula, same data. Okay? So if you can do the plot, you can do the linear model. You just replace plot by LM. LM will not draw anything, but it will give you a result that we can store. We will store it later. But just by a look, we get what is the input, what was the formula, and what are the data. And also will give you what are the coefficients. This is A and this is B. Okay?
Okay.
Okay, no question? Good. Then
can I ask something?
Yes, of course.
Does LM chooses A and B, the best
Yes.
A and B? Oh,
Yes.
okay.
Yes.
So
yes.
it's not because we wrote A weight first and then height first, right? It chooses anyways.
No, but depends on the formula. Here, it is important that you put in that order because this is the model that you're making. You are putting weight as A plus B height. If you put in the other order, you are trying to predict height depending on the weight.
Okay.
Remember, that is the point, that there is one variable that we call the dependent that depends on the others. In this case, the weight is the one that we put in the vertical axis, is the variable that depends on the others. And the horizontal is called independent in the sense that you can control it in theory. But basically, it is okay. This is a little tricky, but simplifying the things a little bit, the independent variables can do whatever they want, and the dependent variables will do what they have to do because they depend on the independent variables. Okay, this is not 100% true, but it's a good way of starting thinking about that. Okay.
Okay. Thank you.
It is not 100% true because, I mean, you have the height that you have. You cannot control that. I cannot stretch you or reduce you. But it will be, for example, if you are doing an experiment, you will be putting, I don't know, more different concentration of sugar or something like that. When you do an experiment, you have something that you are controlling, the concentration of something. That will be your independent variable. And then you will measure something like the growth rate or oxygen consumption or something like that. And that will be the dependent variable. And you will like to connect the input that you give, the independent variable that you control, and observe what was the result in the dependent variable. Therefore, that is why this part is the hard part. I may say something, it's the hard part, but it's also the important part. Everything that will happen later will depend on how you decide to model and what are the variables that you put here. Will you make weight dependent on height? Well, then you can make prediction based on that idea. Will you put sex like a factor here? Well, that will give you another model. So let's see. Weight is here we say, okay, we want to model to predict the weight in kilos given the height in centimeters. Okay, and instead of guessing, we are using experimental data. Now, I have to tell you something. This part of the result depends on your experiment. If you see this class I teach most of the year, if you see in previous year, the numbers are different every year because they correspond to the people in the group, the people in the class. Different years, we have different people and they have different weight and different height and so on. Okay? So this depends on the experiment. The model is philosophical, if you like, it's something that you do based on your knowledge, based on your reasoning, but the values depend on your data. So these are experimental values. I mean, they depend on your experiment. If you do the experiment again, if someone do the same experiment, they may get different values, hopefully not very different. And by the way, my initial guess was -100, and in our case is -84. And my initial guess was 1, and here is 0.8. So I was like 80% correct. No? The real values are 80% of what I say. Fine?
Yeah.
Not bad.
Yes.
Okay, let's make it more amazing so they don't sound so boring. Okay, and then we can use A, B line, and you put the A and B, and you get the line, and you see how they look. Fine? Now, here you see there is something. This is something that you should be always aware. When you write a fixed number, there are two problems. One is that you are working for the computer and not the computer working for you. You have to go and copy and paste. You can make mistakes or something happen. Or most important, if the data change, like it happens to me every year, then this number changes. So this is a slide that I have to update manually every year. How can I do it so the slides are automatic? Or in other words, how can you make a paper that the paper doesn't depend on you updating it? You want the paper updated automatically. We can do this. When you do the linear model, you assign to a variable. So notice, we started saying that we have vectors and data frames. And then now we have formulas. And we also have linear models that are things that we can store. So you can have different kind of things in a variable. A linear model can be stored in a variable, and then you can look at it essentially like you open any variable, but you can also ask interesting questions. For example, you can ask, what is the coefficient? You have the command that essentially the question is, what are the coefficients of model? The coefficient of the model. And you will get a vector with names, and the first will be A and the second will be B. Here you even got better decimals. Okay? So A is the first element of coefficient and B is the second. This is a coef model is a vector, therefore coef model 1 is the first element of the vector and coef 2 is the second element of the vector. Fine? And then you will draw something like this. This time there is no fixed number here. You have the model, you do the plot and then you do the model with the same formula. You see the input of plot and the input of linear model are the same. You assign to a variable that we call model, and then we can use model directly here. Now, if this is too much work, let me show you the real easy way. AB line is smart enough to look inside the model and take the coefficient. So before, after. before, after. Chocolate. You see, this is a very straight thing, very straight thing. You say plot of the variable that you are doing with the data frame, then, I mean, plot what you have in your mind, your model that you have. Then you do model of the same thing, weight and height, the same thing that you do in the plot, and then you do AB line of model. Now I have to warn you, this is not always what you want to do. For the simple case that you have numeric things, it will be fine. But just be careful, because it doesn't always work. Okay, we will see cases that this doesn't work. With models that are a little more complex. For simple model, let's say for simple model like this one, AB line of model works fine. But with model get a little more complex, then you have to be a little more careful. Okay, this is maybe too much blah blah, but let me try to summarize. The second part of the model is the capacity of making prediction. Remember that we said that a model is validated when you make prediction and then you test these predictions. If this is a good model, it should be able to predict what will be the weight of someone that we have not seen before. There is a new student coming today, and we know the height, but we don't know the weight. Can you predict what will be the weight? If the model is fine, we can make a prediction. Okay, I should rewrite this slide. Models are used to make a prediction. So the first part of the model is making a description. The description is the coefficients, okay? The second is to make a prediction. What will be the output when we have new data? So we need to predict for new data. The basic point is that we need to put the new data in a data frame. So you need to do this. This is the tricky part. Tricky in the sense that if you don't use the correct syntax, if you don't use the correct keywords, it will not work. So let me show you. Let me show you. Maybe it's easier if we go here. You have the model that we make with this data frame, and you have weight and height. Now, the basic thing that you have to observe here, the independent variable is height CM. That is a keyword. Now, to make prediction, we use the command predict, fine, based on a model, and then you add new data. So be careful, because this is, I will tell you the typical error that people make in the exam. Instead of data, you have to say new data. Because it's not the original data. This is new data, was not in the initial data. Okay. Then you have to say data frame. This new data has to be a data frame, and the new columns in that data frame should have the same name. This name and this name should be exactly the same. So you copy and paste the name of the independent variable. And then you give one or more value. Here you are free to choose whatever values you want. So in this case, I went one by one, from very short people to very tall people. And I got the same idea, but instead of a line, here we get point by point. So for 155, this is the prediction. This is reality. For 156, there is one that is exactly here. And you see the red points that I'm drawing here, they go forming a straight line. That is why it's called a linear model, because they make straight lines. And it grows with a slope given by B, and eventually if you go to 0, it will cross at A. And what else? Well, essentially it will allow us to make a guess. Of course, this prediction has a big margin of error, but it's better than not having a model. I mean, for example, if I say, look, tomorrow there will be someone coming. He is like 1 meter 90 centimeters. What will be the weight? Well, our guess given this model will be something like 85. So if this person is 40 kilos, we will be very surprised. If it's something like 85 plus minus 20%, I will be fine. So let's put in another context. Let's say that you make a series of experiments with different concentration of sugar, and you have the growth rate of, I don't know, plants. I want to see if plants grow better with sugar, something like that, or aspirin. You know, people put aspirin to make the plants grow bigger. We can plan some experiment. We can make experiment if you want. You know the problem that in biology, experiment always takes several days. So it's hard to make an experiment during the class time. In physics, experiment can be done in a few minutes. But anyway, let's say that we have a plant that you make plant with different concentration of aspirin, let's say. And after that, you plot your data and you make a model. That model will essentially allow you to say, okay, if I have a new plant and I change the concentration of aspirin, I may make a prediction. And you will be not surprised if the result is like this, if the result fits exactly the model. But you will be very surprised if the result is verifiable from the model. That can happen for two reasons. One is because your model is wrong, which can be the case. Or second, because your experiment is wrong. And then you have to be careful to decide what is happening there. In many cases, people say, okay, my experiment is wrong because it doesn't match the model. I have seen that. People say, for example, I was working with someone with the cancer cell lines, and we had different toxins that were killing the cell lines, and we had an expected result, and the experiment was contradicting the expected result. So we had two options. Either we did the experiment wrong, or the model is wrong. And we tried to prove that the model was wrong, but we could not convince the peer review. People believe that the experiment was wrong. But that is how we do science. We have a model and we have a result, and we try to see if the model improves with the new data or not. So let me show you an experiment that I did, and let's start with a basic thing. This is an experiment that I normally do in the classroom, but not this year because we don't have classroom. Coils. Maybe I have a rubber band. Well, anyway, that you know what's a coil, no? Or for practical things, I used to use. Well, sometimes I use this, the coil from the book, and sometimes I use elastic. I have them somewhere. But okay, let's try to do it without too much animation. So what is the relationship between the force that you make here and the extension? So you have a natural length here, and then you put weight, the coil will grow. And you care about this difference, okay? Do you know the answer to this? Did someone tell you about this sometime in your life, the relationship between force and the size of the elastic?
It's been a long time. I don't remember.
So you didn't learn. You just studied, but you didn't learn.
I guess.
Yeah, because I also studied many time ago, but I never forgot it.
But I hated physics. That might be the reason. Yeah.
If you hate physics, then you will never be a good molecular biologist. Physics is the easy part. Molecular biology is like physics, but really hard, really hard. In physics, things are easy in general. In biology, nothing is easy.
For me, it is the opposite. Physics is so hard for me.
You will see. You will see. The experimental physics are in general very straightforward. Then you go to the analysis. In biology, experiments are so hard that people don't get to the analysis. But when you get to the analysis, you will see that they are many times harder. Let's say that in physics, linear models correspond to reality. In biology, often they don't correspond. Biology tends to be very nonlinear. It's very complicated. Experiment may be easier, but I'm not even sure. At some level, physics is the mother of science. You know, is the model that we try to approach. We try to do science like physicists do, which is hard, of course. Physics is a easier subject in general. Okay, so this is called Hooke's law, invented by Robert Hooke, that you should know. Do you know Robert Hooke? Okay, this is an easy question. This is a history question.
Yes, we know.
Hmm?
Yes.
You know? Why you know him?
He did something about telescopes and microscopes, I think. I remember.
Yes, sir. He kind of invented this microscope. This is the Hooke microscope. So this is essentially biology. This is what biologists do. They make microscopes. Okay, no, physicists do microscope, but he did a microscope to do. The point is this, that we can only measure physical things. And biology, we cannot measure directly biology. We can measure only physical effects of biology, like weight or oxygen consumption or electrical things. We can only measure physical quantities. And biology is kind of a particular corner of physics in that case. Okay, so some comment. This is the only portrait we have of Hooke, and we are not even sure if it's the correct one. So here you see he's studying nature, studying this. This is a very nice thing. We will talk about this later. And you have a coil here. So he was a natural philosophist and a polymath. Math here is not mathematics, it's knowledge or learning. Math is learning. And a biologist. So this is biology. And the reason why we don't know him very much is because he was in a British Royal Academy of Science at the same time of Newton. And Newton was so much arrogant, so much himself, that I am the genius and everybody's stupid, that he hated Hooke, and he ordered to destroy all the portrait of Hooke. And essentially, he wanted Hooke to be deleted from history. So we know very little about Hooke because Newton was the enemy. Okay, so how we model a coil? Hooke law essentially translates to this thing. The coil has two values that we want to find. One is the length of the coil, or the length of the elastic, if you like. I do it with the rubber gums. And then if you apply force, you will have this change of length. Okay, we can discuss this, but essentially the force here is negative because it's pulling to the inside. And you have the natural length and you have the physical length. So you have the difference between the natural length and the real length, and that difference will be proportional with a k proportional rate to the force. The more force you make, the more difference will be. So essentially, here you have to see the difference between the original length. I mean, maybe I can do with this. The original length, and if I pull, it will grow until it breaks. I don't know. But if I pull, it grows. Well, let me find elastic. Well, let's make it a video. Let's make a little thing. I will stop sharing for 1 second because I want to share again. But this time I'm going to optimize for video clip. This one, optimize for video clip, not sound, because there is no sound in this video. So I don't know, I never tried this, but let's see. So I made the experiment and I made a video, and I will give you the link later. No? So let's see. So I didn't test, but I essentially make this animation, you know. Maybe I move it too much, but you see that was essentially the experiment. I put some balls, some marbles, and they and every time I measure the difference. So the summary is this one. Okay, let me go back to the normal because this is kind of high performance. Let's stop and share the screen again, but not the high speed. Okay, so essentially I have this is a different experiment because I use the different cup. But I have something to hold the cup, elastic, a clip, and a cup, and I put this, what is the name, marbles, and I measure the length with a tool, and I register it in a piece of paper that was my notebook. And then I transfer it to the computer. Okay? And I got this. And if you want, you can get the data here. So usually in the classroom, I give people elastic and we try to do it physically in the lab. Maybe I should ask you to get elastic and get coins. You can do with coins. So I measured this in millimeters. The tool gave me a couple of decimals in millimeters. It was a nice tool. And I did it twice. I did it twice for well, I should have done more than twice, to be honest. But I did it twice, first because I didn't have the time to do it again. Second, because I wanted to make sure that that the thing was replicable. The idea of replicability. If you can do it again and you will get the same result again and again. And third, because I want to protect myself from errors. And fourth, because I wanted to know my margin of error. Well, in fact, I made a mistake. After I did the experiment, I realized at first that I didn't took all notes. My learning on that experiment is that I should have made a video, not a high-speed video, but a normal speed video. Because in the video, I can see if I am doing things right or wrong. For example, if you see the second time I forgot to write the weight with one ball. I have 0, 1 here, but I don't have it here. Then I have 2, 3, 4, 2, 3, 4. There are more data that I didn't show you here because it doesn't fit in the screen. But there is these 3 columns: number of balls, length, and repetition. Now, you should know something. Maybe I have some here. The elastic has a basic problem. Oh, no, I don't have. that when you pull it, when you, let's see with this one, if I pull it, it's easy to measure the length, okay? And the more I pull it, I can. But if I don't pull it, it is very hard to measure the length because it folds, no? Elastic had that problem that it is very hard to measure the natural length. You follow me, no? If you don't follow me, I can show you with a real elastic. So what I mean is this: when I put some weight here, when I put some weight, I will have the elastic in a vertical line, and it will be easy to measure. But if the cup is empty, or if there is no cup, the elastic will be a circle. And measuring the length of the circle is very hard. You want to measure in a straight line. So the two values that we want to find here, this L and K, are not straightforward. They are not in the numbers, but they are in the model. So this is how I plot them. Okay, you plot the length depending on the number of balls. So from 0 to 7, I have in the data. And in some cases, I have 2 copies. In some cases, I have only 1. And they are similar, but not identical. So there is some variability here. Okay. So how we model this thing? Well, there are a couple of ways. Essentially, you can make length depending on the number of balls, or balls depending on the length. In this case, I went with the natural way because the number of balls is the part that I control. It's the independent variable. I can put 1, 2, 3, or 0. It's up to us how many balls we put. Is the parameter that we control. And the length is the result of the experiment. Okay? Then we get 2 values, 76 and 5. What is this? No, this model is not. Okay, no, I will skip one slide here because this is not the correct model. So here, this is the physical interpretation. So if the force, if this is the original formula by Hooke, in our case, the force depends on the mass, the gravity constant, and the number of balls. Do you agree with this? This is, again, physics, but it depends on the total mass is the mass of every ball times the number of balls. Okay, if I have 2, I have twice. If I 4 times. Agree? And G is the gravity constant that essentially changing the changing of unit between the mass, between the kilos or grams into the force. Okay, and then you have K with some units, and the length that in this case was millimeters. Tamam. So if you play a little with the formula, you get I mean, essentially, you multiply the things and you move, and you get this. The formula that we are our model has 2 parts, A and B, and A will be the natural length of the elastic, the length of the elastic without any extra, and B will be this part, the mass of the balls times gravity constant divided by K. And the mass is something that we can measure independently, and K is what we want. K is called the elasticity constant. Maybe I put it before. Is what makes, if the elastic are very soft or very hard, the elasticity constant will reflect that. You know, for example, sometimes the elastic are very flexible. For example, this is not very elastic. It's a high elasticity constant. I have to pull it a lot if I want to take out. And by the way, this elasticity constant apply in many contexts. For example, when you make a building and you put steel, the steel that holds a bridge or holds a building, it's also measured with an elasticity constant. Last year, I was working with some colleagues from the physics department. We were trying to model the eye, and you need to consider the elasticity of the eye, or things like that. Okay, but this is the easy case because we are moving in one dimension. So this will be our interpretation. The A will be the length and B will be connected to the constant, the elasticity constant. So we take the first coefficient and I say the length of the coil was 76 millimeter, the length of the elastic without any ball is 76. Remember, I say that in real life it's hard to measure this thing, but I can do it indirectly with, in fact, I have another experiment. I will show you more experiments eventually. There are many experiments that are easy to do, more or less easy to do, that can allow us to measure this thing. So we get something about the coil and something else here. Here you have to be careful. The coefficient of model is a named vector. Well, the name is n volts, is the name of the coefficient, the name of the variable that you are using. And here I weighted some of these balls and they were like 20 grams. And then I multiplied by by G, the gravity acceleration, and I get the elasticity constant. Now, this name n balls is not a good name there, but you will get it. I mean, if you want, since this part has name and this number don't have name, you end with the wrong name. But don't care about the name, just care about the number. So essentially, this is the result. This is the result. I have some. Yeah, there is some people wrote the number wrong in the exam. That was the thing I wanted to say. Well, I have not taken a deep look at your exams. Let's talk about the exam for a second. Let's see if I have where I have your exam.